Hey, it's Mr. Lum again, and we're going to be talking some more electrochemistry, but this time we're going to be talking about something a little bit different, and that is non-spontaneous reactions, or in other words, electrolysis, or an electrolytic cell. So, electrolysis is when we use external power to cause a non-spontaneous redox reaction to occur. So, we have here is we're plugging in something. We're using a cell or a battery or some kind of direct current in order to make a non-spontaneous reaction happen. And that's what electrolysis is. Now, an electrolytic cell is just simply a device where electrolysis can occur. So here we have an example of an electrolytic cell. Now, there are three types of electrolytic cells, and this is going to be the first type. This is electrolysis of a molten, and I spelled molten wrong, but you know, whatever, of a molten binary salt. Okay, now binary salt is just a salt that contains two types of ions, like KCl, MgBr, AlF. These are a bunch of examples of molten salts. It has a positive ion here and a negative ion here. So what we do is we melt this salt, we make it liquid, and then we put in these non-reactive electrodes. Now, the electrodes are usually made out of, so I'll write this right here, electrodes are usually made out of something like carbon or platinum. The reason why they're made out of carbon and platinum is because carbon and platinum don't react with anything. They're very, very unreactive. Okay, so we can write that down there. The reason why we use these for the electrodes, because they're unreactive. So these are, again, before when we had our electrochemical cell, those were usually two different types of metals. Here we can have the same type of metal, like platinum, 2 bars of platinum here, and the reason why we use them is because they're not going to react. Now, in this liquid right here, we have KBr. Again, it's not in solution, it's molten, it's melted. And so here we have our KBr in here. So this is going to be K plus and Br minus in here in molten liquid. Now, here is our cell. Now, here's a few interesting symbol for cell. Whenever you have a cell like this, the big line always means positive. It means the positive end. The little line always means negative. Okay? So here's the little line on this side. This side I drew it opposite, so the small line is negative. But here it is on this side. Now, whenever you have the negative side on here, electrons will always leave the negative side. So for this particular cell right here, electrons are moving in this direction. Okay? And they're going in on this direction. So what kind of electrode is this? Well, this electrode is gaining electrons. So if this electrode is gaining electrons, since it is gaining electrons, what is happening there is reduction, and therefore it is the cathode. So this right here is the cathode. This one is losing electrons. Electrons are leaving here, and therefore this is the anode. Okay, electrons are leaving here. Now, since electrons are coming here, coming into the cathode, it makes the cathode negative. And so in our molten binary salt right here, we have K plus and we have Br minus. So this is gaining electrons, therefore this becomes negative, and K plus, or the positive ion, is attracted to this negative electrode, or this negative cathode. And so K plus is attracted to right here. And Br minus is attracted to right here. So what is happening is that K plus is turning into K right here. K solid, okay? So K plus is turning into K solid on this cathode right here. And Br minus, so here's our reaction right here, Br minus is turning into bromine liquid and 2 electrons. Now what we need to do is we're just going to balance this, so I'm going to multiply this one by 2. So this is going to be 2, 2, I should have forgot to write the negative sign there, and 2. Okay, so that means our electrons, when we add these together to make our full redox reaction, these are going to cancel out, and our full redox reaction is 2 K plus plus now, so here's our full redox reaction right here. Now let's talk about how much electricity, how much energy this takes for this reaction to happen. So again, our E naught, I'm kind of running out of room right here, but I'll write it up here. If you remember this formula, our E naught cell equals our cathode minus our anode. So I'm going to use this formula right here and plug in our values to see how much energy we need for this reaction to happen. So our E naught cell is going to equal our cathode, and what we said was our cathode is this one right here, and the reaction that's happening at it is our K plus. So our E naught cell is our cathode, which is minus 2.93, minus our anode. Okay, and the reaction that's happening at our anode is Br minus right here. So minus, and it's just 1.09. Okay, so we should have you should have learnt this formula in the previous video. So E naught cell equals cathode minus anode. The cathode reaction is K plus right here. The anode reaction is the Br minus. So I'm just going cathode minus 2.93 minus our 1.09, and so therefore our the amount of energy that this requires is negative 4.02 volts. So what does this mean? Well, since it's negative, we know that it means it's a non-spontaneous reaction. And what this number means, it says that it at least needs 4.02 volts just to start. So you probably actually need more than 4.02 volts of electricity to get this reaction going, but you do need at least this. So if you're just adding, if your battery is only putting out 3 volts of electricity, well, nothing's going to happen. It has to be putting out at least 4.02 volts to start going.